Okay, so the second video in inverse trig is going to give us functions, or we're going to be integrating functions whose results will be the inverse trig functions. And the nice thing here is that because all of the cofunctions are just negative of the normal functions, really you only have three antiderivatives to worry about: arcsine, arctangent, and arcsecant. Because if you had a negative coefficient, you just put the negative in front, and so you could write an equivalency, I suppose, if you wanted to, but the standard three functions and the ones you'll see in the AP exam would be arcsine, arctangent, and arcsecant. And again, notice sort of the structure here, and the general form for these functions that we're going to take antiderivatives of are going to really be like looking for squares. And the thing is that only one of the squares will be a variable. So in this case, it's the u. U is our generic variable here. The other one is a constant, and it doesn't always have to be a squared, but you're going to treat it as a square because in the antiderivative, it is a square root will come out. So, and one thing I also want you to notice is that arcsine is the only one that does not have 1 over a, where arctan and arcsecant do. So, a good rule of thumb here is that if you see something's quadratic in the denominator, but not linear in the numerator, not something where you can do a u substitution, then it's going to be an arc function, arc trig. So like, for example, here, I know this can't be a u substitution because if I let u equal this, if you let u equal 9 minus x squared, the derivative is negative 2x dx. This is more like, this is 2 degrees off, not 1 degree. Remember, a derivative would take like 1 degree off. I also know it's just not it's not going to be natural log because it's not just 1 over x, even though I have a reciprocal function, or even though I have a function in the denominator. So my thought process then is, if I don't recognize its u substitution, it's not going to be a natural log, then our next kind of line of defense is it an inverse trig function? So we have to think trig, and it is. It's inverse. It's going to result in an arc sine function. And so sometimes it's helpful to also identify not only the u, but also the a. So so in this case, my u is just my x, which means du is dx, which is nice. And then since 9 is in the a squared position, I'm going to say that a is 3. So this could be rewritten as du over the square root of 3 squared, or like a squared, or you could think of it as 3 squared. I go back and forth on what's easier, looking for that structure, or what makes sense to you. I just like that I know that it's 3 squared minus u squared, because the antiderivative, that's a du there, and whether you put a du there or like a 1 du, doesn't matter. But the antiderivative, there's not 1 over a, but it's just going to be arc sine of u over a, so 3 plus c, and in this case u is x. So arc sine of x over 3 plus c. So again, that example just kind of recognizing when would you use, or how would you know that to think these are inverse trig. And a good clue is that you have quadratic in the bottom, but not a linear function. It's a constant function on top. Okay, same thing with number 10. I'm noticing it's quadratic in the denominator, but the numerator is 2 degrees off. It's just the constant 1, understood 1 sitting there. So this then my thought should go into trig, inverse trig, and there are no square roots, so I'm thinking arctangent. And arctangent, like this thing, the 16x squared would be u squared. So what makes a good u would be 4x, because, right, 4x as a quantity squared would have been that 16x squared. So I'm going to let u be my 4x. Its derivative would be 4 dx. Notice I just have a dx, so I need a 1/4 here. And then my a value is 1. So now I've got 1/4. And then it's 1 over 1 squared plus u squared du. And the antiderivative, we have 1/4. Now it is 1 over a, so I'm going to put 1 over 1 just to remind myself that if a weren't a 1, I would have something there. Arctan of u over 1 plus c. And then what was u? It was 4x. So I have 1/4, if I simplify the coefficients in front, arctangent of 4x plus c. So again, even if you thought, oh, that's so easy, I didn't need to use substitution, I still think you should get in the habit because, just making sure you have everything lined up and knowing what is the u and what is the a. Okay, now here, I'm looking, I have x to the 10th power, and I have 5x to the 4th power. So clearly more than 1 degree off. So a simple u substitution won't work here. But then I'm thinking of squares. I have 16 a square, and x to the 10th, really that's x to the 5th squared. So that might make a good u. If u is x to the 5th, its derivative is 5x to the 4th dx, which, how convenient, it's sitting right there. And 16 is 4 squared, so making a equal to 4 seems to be a good thing. So now we can rewrite this. It's the antiderivative. That's just a du divided by 4 squared minus u squared. And again, because we chose x to the 5th to be my u, x to the 5th squared would have been x to the 10th. So that lines up perfectly. Difference of squares here in the square root, this is arc sine. And again, arc sine does not have 1 over a. So it's just going to be arc sine of u over a, and then plus c. And then our u was x to the 5th. So arc sine of x to the 5th over 4 plus c. Okay, next example. It probably should be time to have an arcsecant, and we have this characteristic, a coefficient or an x out in front and here, and we have to be really careful is that when you integrate and line up for arcsecant, you need this value. If this is your u, this needs to be identically that's u squared. So we have to make sure this lines up nicely. So I'm going to start on the interior here and make this, this is my u squared, which means u would have been 2x. So u is 2x because that quantity squared would be 4x squared. So du is 2 dx, and I only have a dx, so I need 1/2 du is equal to dx. 25 should be clear that a is 5. And so that accounts for this, that accounts for this. But what it doesn't account for just yet is this x. So according to that, x is equal to u over 2. So I'm going to have to do, just kind of like a variation there of that x. So x, oops, I thought I picked red. Not that it matters. So x is u over 2. So that much right there becomes u over 2. Then this is the square root of u squared minus 5 squared. And then we need a 1/2 du. So 1/2 du. Now, if you want to kind of maybe simplify this a bit before we do the integral, so like looking at your layers of your fraction, just be really careful. So we've got du, and then the square root of u squared minus 5 squared. Now, this 2, like the 1/2, is really like a 1/2. So that actually is going to cancel. This 2 and that 2 actually are going to cancel. So it's just going to be this, which actually works out really nice. So it ends up, again, that's what I mean, whether that canceled or not, I still would be able to do this. But now I don't have to worry about the coefficient, which is really cool. So this is definitely arcsecant. So there is a 1 over a, so 1 over 5 arcsecant. And that's the absolute value of u over 5, like that, plus c. And only the function is in absolute value, although here it's positive anyway, so it doesn't really matter. And what was our u? It was equal to 2x. So we have 1/5 arcsecant of 2x over 5 plus c. Okay, so again, the sooner you can commit those to memory, the better. The next example, again, this, I see 6x and the 3x, and I'm thinking, oh, 3x squared would be 6x. So this, again, is a sum of squares. Let's let u equal e to the 3x. And it's a bit deceptive because there is a e to the 3x here, but that's not the u I'm intending it, right? Because e to the 3x would be its own derivative, just off by a factor of 3 by the chain rule. So we're going to multiply the 1/3 over. So 1/3 du is equal to e to the 3x dx. So that's sitting right there. A is 1. So this looks like it fits the perfect structure of arctangent. So 1 over 1 squared plus u squared du, which this 1/3 just is part of our coefficient. Remember, arctangent is 1 over a, so I'm going to put 1 over 1. Arctangent of u over 1 plus c, and u was e to the 3x. So 1/3 arctangent of e to the 3x plus c. And you might be automatically thinking arctangent because we're in the arctangent section, but when all of your all of your integrals are mixed up, you should go through what order of, like, okay, is this a simple power rule? Is there a u substitution? Is this natural log? Or now has it become arc trig? And this was tangent because there's no square root. Again, trying to look at the degree of the fourth power versus just 1. So this clearly can't be a u substitution, but t to the fourth power is t squared. So that might make a good u. U is t squared. Du could be 2t dt. I have 4, so I need 2 du is equal to 4t dt. And in this case, again, a is equal to 1. So this would fit the structure. So I've got 2 du, the square root of 1 minus u squared. So this fits the structure of arc sine. And there is no 1 over a, so we just have the 2. Arc sine of u over a plus c. Now, if it's a simple substitution like this, you don't have to necessarily show u over a each time, but I like doing that simply because it's just reinforcing that formula. Plus c. Okay. Now, I'm smiling here because I'm really excited about the next two, because this is quadratic, right? This is quadratic without a linear term up top, so this has to be arc trig. There isn't a square root, so this has to be arctangent. But the problem is arctangent is u squared plus a squared. There's no middle term. And if you know me from the past here, you know how much, like, what I really love to do. You'll know why I was smiling, because I like to do completing the square, right? We get to complete the square on this. So I hope you're just as excited as I am. So let's complete the square before we integrate. Because when you can complete the square, you can get a sum of squares. So it's x squared minus 6x, and we'll push the 13 down just a bit. So half of 6 is 3, and then 3 squared is 9. So we're going to add 9, but immediately subtract 9, so it balances. And then we're going to just see how cool this is. All right, so dx, and this is the quantity x minus 3 squared. And I was really nice to you. That's 4, perfect square. It doesn't have to always work out that way. But now my u can be this expression x minus 3, right? So if I let u equal x minus 3, the derivative is just dx, which is great. That's what I have. And 4, that's 2 squared, so let a be 2. So this becomes the antiderivative of du divided by u squared plus 2 squared. Now remember, arctangent is 1 over a. It's one of the first times we actually had an a that was not 1. So it's 1 over 2 arctangent of u over a, which was 2, plus c. And then again, u was x minus 3. So, again, you see a quadratic but you've got that, it's like a squared plus bx plus c, then complete the square. So it's 1/2 arctan of x minus 3 over 2 plus c. Okay, and then of course let's do one more with bounds, right? Again, I'm noticing quadratic, not a u substitution. Can't even break it up into different fractions. So let's complete the square. So that would be dx over, and then that's x squared plus 10x. Half of 10 is 5, and 5 squared is 25. But then we must immediately subtract 25 from 106. And I still have bounds of -5 to 4. But now, again, what I think was pretty nice to you in this example as well, that when you sum that up, you get 81, which ends up being a nice perfect square. And this is x plus 5 as a quantity squared plus 81. And so let's do a u substitution. So we let u equal x plus 5. The derivative is just dx, which is great. And in this case, our a value is equal to 9. So let's do a change of bounds too, since everything's in terms of u, because we have du, and we have got u squared plus 9 squared. So if u really is x plus 5, then -5 becomes 0, and 4 plus 5 becomes 9. So now I don't even have to worry about x's anymore, and it's 1 over a. And notice the since a was not u or x, right? A stays, so it's going to be 1 over 9 arc tangent of u, which I could keep as u, over 9. Instead of saying plus c, it's going to be evaluated from 0 to 9. 0 to 9. And so this is equal to 1/9 arc tangent of 9 over 9, which is 1, minus 1/9 arc tangent of 0. Now, we should recognize both of these ratios. Arc tangent of 1, what kind of angle has a tangent ratio is equal to 1? And since it's the principal angle, right, arc tangent is given, that's pi fourths. So now I've got 1/9 times pi fourths minus, and then arctangent of 0 would be 0, so minus 0. So this is equal to pi over 36. And, again, I just think about, like, what did we just do geometrically? Like, geometrically, we found the area under this curve, right, which is a rational function. So I could graph this from -5 to 4, and whatever from -5 to 4, whatever that looks like, some kind of rational function. But the area, whatever that curve is, has it's pi over 36. I lost it. There it is. Almost there. So again, to me, that's just so cool that you have a finite length, a base of 9, right, from -5 up to 4, yet its area is pi 36. And like, at first glance, you wouldn't think there'd be any pi's there anyway. So it's kind of a cool thing. Okay, so again, that video is to give us another strategy to take integrals. And the results, or the antiderivatives, will be the inverse trig functions. Not to be confused with integrating inverse trig, which we will eventually, but again, that's that technique of integration by parts, which we will learn in Chapter 7.